Yes. Okay. So I think we are live. We are live on YouTube as well. So I think this is a very good time to start our class. So first of all, congratulations on finishing 2023, and we are going to finish it on a high note. And we're going to learn something new today. And I have changed the page a little bit with the AMC logo at the as a watermark on this page on this note. So, after the class, maybe, I'll send this particular document as class note. But you need to also, like try to take some notes, running notes. And at the end of the class, of course, like every time, there will be an attendance sheet. So you have to fill up that attendance sheet. One or two questions will be there in that attendance sheet. Now, having said that, let's dive directly to the topic of today's class. So today we are going to learn about RSA, right? So RSA is an algorithm, right? So this algorithm is it's in cryptography. And the RSA, the name of RSA, the acronym RSA comes from the names of three different, let's say, scientists, right? Or maybe computer scientists. All computer scientists are mathematicians at some level. So, like extract what message you were trying to send to me. So the cycle is that the message, right? The message. Let's give some name to this message. Let's name this message as, let's say, M, right? Let's name this message as M. So this message M is converted into a cipher. So let's name this cipher as C, right? And after after this when the recipient wants to read this message, this cipher C is again converted into the message M. So it's a very simple concept, right? Message, you convert it into a cipher, and then again the cipher gets converted into the message. It's a very simple thing. Very similar to what this Happy New Year was about, right? In this crypto system, what happened is that there is a message Happy New Year. We reverted the number. There is an algorithm here, right? There is an algorithm. For example, if I want to send you a message like hello, right? So hello will be converted to OLLEH. And then this OLLEH that I'm writing on the top right corner will be read by you as hello. Because you know that the process of converting a message to the cipher is by, like writing the word in a reverse manner. Right? Okay. All right. So, since you know about this now, what we can do is we can now go into the math and try to identify, or try to define some functions. Let's try to define some functions so that this process is being well represented in a quantitative way, right? Okay. So the crux of the matter. Yeah. Okay. So what we'll do is that we will look into we will try to identify what in a few cryptographic elements, right? So let's call them some cryptographic elements are there. Cryptographic cryptographic elements. Correct? Now, the cryptographic elements, so this is how I'm going to tell you. It's a new concept. It's a new concept for you. You have maybe not learned this kind of concepts in this course or in a course before this. But of course, like when you go to try to understand algorithms, data structures, this kind of approach will be really very familiar with you. So as of now, what we'll do is that we'll define a few cryptographic elements. Correct? So, the first cryptographic element that we are going to talk about is called a public key. All right. And the second cryptographic element that we are going to talk about is called a private key. Now, very similar, I'll make this very clear to you, right? How do I make it clear to you? Look, let's try to identify. Let's try to like talk through emails, right? So there is a person A and there is a person B. Yes, please. Is it so? So since the beginning it is echoing or is it echoing just now? Okay, thank you for pointing it out. I'm going to change that scenario. Okay, that's why Rahil is very important in my class. Oh, or is it echoing?
No, sir, it's proper, sir.
It's proper. Okay, thank you. All right. So, um, yeah. So let's. So we are talking about we are talking about uh, two people, two persons, A and B, with they have their own email IDs, right? And they have got their own mailboxes. So A wants to send an email to B, right? And between A and B, you see this huge space. This space is the internet, and all sorts of things happen in the internet, right? All sorts of phishing, uh, hacking, and like eavesdropping, all kinds of like breaking of protocol, trying to steal information. All of these things happen in this space, in the yellow space. So A wants to send one information to B and does not want anyone in between. Like let's give them a name. Let's name that C, right? So A and B do not want C to know what information is being sent from A to B. Correct? So what they do is that it's very simple. They go and create an email address, right? They go and create an email address. So let's say that email address of A is email A, and every email address has a password, PSWD, password, password of A, right? So the email address of A, you put the email address of A, you put the password of A, then only the email box of the inbox or the sent emails or the trash or other emails of A will open. Correct. And similarly, there is an email ID for B, and that also has got a password, right? PSWD underscore B is the password, and email underscore B is the email. Now, now if you notice very carefully, from general knowledge, we know that the email of A and the email of B are known to everyone. There is no harm in sharing the emails. Sometimes while writing the email address, let's say some I want to share my email ID with you, right? So I might say that my email, right? And then instead of at the rate, I'll write at, right? At gmail dot dot. We write this email address in this way to protect our inboxes from unnecessary emails. But we are open to share our email IDs with everyone. But my password to this email ID, my email at gmail.com, is very private to me, right? So that tells us that when we have a system, this system comprises of a person A, a person B, and the eavesdropper or the hacker or a fisher on the big in the middle called C. So this email A, email B are known to all A, B, and C, right? So this is a public key, right? The cryptographic element in this case is a public key, which is the email address. So I'll just write down here Example, email ID. The email address is known to everyone. It's a public key, right? The address to my home is known to everyone. Everyone knows that I live at Calcare, right? But the key to my home, the key to the door to my home is a private entity, right? So that element, that cryptographic element is called the private key. And in this case, in the case of the picture that you can see on the right side of the screen, right, the password A, PSWD-A, right, this PSWD-A is known only by A. And on the other hand, let's use maybe pink, right? So, no, not pink, let's use green. So this B will know the password B, right? So um, email ID A, email ID B is known by A, B, C, everyone. Whereas the password of A is known by A and A only. Password of B is known by B and B only. Right? So this is an example of private key. Right? Okay. So now we know that there is a public key and there is a private. How, like we can define these entities, this cryptographic entities in math, and try to see what how we can actually run this RSA algorithm, right? Okay. Now you see the logic. There's a logic here. The logic is goes as follows. So initially, what we'll do is that so email ID and password, right? So if there's a person A and person B who want to communicate, they need to create their email IDs, right? So that process is called key generation. Key generation, right? So the key generation has got a mathematics behind it. We are going to learn that, and as a little teaser to what we are going to learn, we are going to use prime numbers for this key generation. Okay. Now, having said that, once we have generated the key, what we will do is that we'll take a message, right? We'll take a message, message. We'll take a message, right? And using the keys, we are going to encrypt. We're going to do the process of encryption. Encryption. We'll do this encryption. This encryption has got its own mathematical method of doing it, right? Once you encrypt the message, it becomes a cipher. CIPHER, right? The same word we learned a little while back. A message is converted to cipher through encryption. And once the cipher has been created, we will again transform that to the message by the process of decryption. DECRYPTION. Correct? So we are going to take a take generate a key, a pair of keys, right? When we are generating keys, we are generating both the private and the public key, right? So when you are creating an email ID, you create the email ID and the password. When you are making a lock, you make the lock and a key, correct? So when it's same as when you're getting on the bus, you get up on the bus and then get down from the bus, correct? So for example, there is a bus stand A and bus stand B. So there are people getting up on the bus. When the bus is moving on the road, I do not know who is there inside the bus. So that's also kind of an encryption. When people get down from the bus, I get to know that Rahil is getting down from the bus, right? So we'll first generate the key. We'll use mathematics for doing that. There is a mathematics involved in encryption of a particular message, and there is a mathematics involved in the decryption of the message again. Now, again, this message is going to be a number, right? Actually, whenever there is a real world situation, the alphabets are there, the words are there are sentences, there are pictures, everything can be converted into a numeric message, right? The number could be of base 2 when it is called a binary. The number could be of the base 8 when it is called an octal number.
The number could be of the base 10 with the digits from 0, 1, 2, 3 through 9. So it is called a decimal number. The number could be a hexadecimal number, which is of very common use. If you look at the MAC address of your computer, of your mobile phone, of your smartphone, or maybe your Bluetooth speakers, right? You'll find out that there is a MAC address, and it has got the digits are 0, 1, 2, 3, normal 9 digits are there, then A, B, C, D, E, F, right? So these are the digits. There are 16 digits in total. The base is 16 over there. So every data can be converted. Every data message data can be converted into a number. So we take that number as a message, and using the keys we will encrypt the message, and then we'll decrypt the message. And that is how the questions are going to be set in your exam. And this is a basic knowledge that we all should have. Okay, so having said that, let's now delve a little bit more into the mathematical background, and try to and then we'll directly jump to the algorithm, and we'll maybe solve the problem together. Okay, so before going into so the first thing that we should recall when we're doing the math behind this encryption and decryption is as follows. Okay, so let me try to draw a line here. Ooh, nice. Okay, so first of all, we know that if P is a prime number, if P is a prime number, right? Then P has to be, then there are a few properties, right? So the one property is that P has to be strictly greater than 0, right? And P has to be an integer. P has to be an integer. We do not have a provision of having a prime number which has a non-zero decimal, right? So 7.3, it cannot be a prime number. 7 is a prime number, 3 is a prime number, 7.3 is not a prime number. It is not an integer. Negative 7. 7 is a prime number, but negative 7 is not a prime number. It's a negative number. Come on. Okay. And also, if you have a prime number, one of the most important characteristics is that the factors or the divisors, right? We use the word factors, but like more specifically in this module, I would recommend you to use the word divisors, right? So the divisors are 1 and P. There are just two divisors only, right? So there are just two divisors. Okay, this is known to everyone. All right, let's move to the next mathematical background that we need. As I said, this module has got no calculus, so there is no crying. Okay. Now, we have also done this problem in the lab experiments, where we had noticed that if there are two prime numbers, if there are two numbers A and B, right, and if there are two integers, we are just talking about integers. There is no decimal number, and no calculus, right? No decimal numbers. All these are integers. So, if there are two numbers A and B such that the GCD of A and B is equal to 1, right? Then there are two numbers A and B, two integers A and B, whose GCD is 1, which means that you look at all the divisors of A, all the divisors of B, and you see the common divisors. Out of those common divisors, if if there is just one divisor, one divides every number. So if the divisor, the greatest common divisor is 1, if the GCD of A and B is equal to 1, then we will say that A and B are co-prime, right? So, but by the way, A and B, they need not be prime themselves. As a small example, let's consider a small example where A is equal to, let's say, 2 to the power 3, which is equal to 8, right? And B is equal to, let's say, 3 to the power 2, which is 9, right? So none of them are prime numbers, but GCD of A comma B is equal to 1. So A and B are co-prime numbers over here, right? So they do not have any common divisor except one. Okay. Now that we have understood we have revised what a prime number is, we have understood that okay, when do we say that two numbers are co-prime? Let's now move on to a very new introduction. Let me introduce you to an amazing function, right? So this function is called the Euler, Euler, or Euler, whatever you want to say. I love to say Euler. Euler's totient function. Totient function. All right. Euler totient function. Now this function is a very interesting function. So this function is is represented with this letter phi. This is phi. This is a small phi. Phi. Right. Phi. And we and the input to this function is basically a number, right? Any integer, any positive integer. Of course we'll consider positive integers here. We won't go to negative integers in this case, right? So only non-zero, non-negative, which means positive integers, are allowed here. So the description of this function is the the description is as follows: the number of positive integers, positive integers less than n that divide n, right? So what we're doing is that we're counting, given a number, we'll just uh, well, not that divide n, that do not divide n, my bad, that are co-prime with n, my bad, please forgive me for this small mistake, that are co-prime, to with n, the co-prime with or to n, right? So uh, let's take an example and try to understand this function, and then we'll return back to the formula, right? There's a formula for this number. Okay. Let's take an example. So let's take the numbers, let's say 8, right? So we'll count. So what are the numbers less than 8? We have got 1, 2, 3, 4, uh, or maybe let's reduce the number because I have got a very less space on the screen. So let's make it 6. Okay. 5, right? So these are the 5 numbers which are less than 6. Now we want to check whether check which of these 1, 2, 3, 4, 5 are co-prime with 6, right? Or co-prime to 6. What does co-prime mean? Co-prime means that the GCD of we have to find out the GCD of 1 and 6, right? GCD of 1 and 6, and then after that we'll find out the GCD of 2 and 6, right? After that again we'll find out the GCD of 3 and 6. After that we'll find out the GCD of 4 and 6. After that again we'll find out the GCD of 5 and 6. Right, let's write down the values. So GCD of 1 and 6 is 1. GCD of 1 with any number is 1. GCD of 3 and 6 is 3 because 3 is the divisor of both of these numbers. Right? It's greater than 1. Again, GCD of 5 and 6 is 1 because, well, the divisors of 5 are 1 and 5. It's a prime number. So whenever we have a prime number, the GCD of that prime number with any other number, unless that number is a multiple of 5, of course, multiple of the prime number, it is going to be 1. In this case, 6 is not a multiple of 5, so GCD of 5 and 6 is 1. Right? So the common HCF, or highest common factor, maybe that's how we have learned in school. We use the word GCD over here. It is equal to 1. right? Okay, two of these pairs are remaining, 2 and 6. So 2 and 6, 2 divide 6, right? So 2 is a factor, 2 is a divisor of 6, and 2 is its own divisor as well. So this is equal to 2, and GCD of 4 and 6 is also equal to 2, because 4, well, the divisors of 4 are 1, 2, 4, and the divisors of 6 are 1, 2, 6. 1, 2, 3, 6. The common divisors are 1 and 2, out of which 2 is the greatest of them. So 2 is a GCD of 4 and 6. So that's the logic, right? Okay. Now we are interested in counting how many are co-prime, right, with the input number. So for co-prime, the condition is that the GCD has to be 1. And you see that there are just two places where the GCD is equal to 1, right? They're just two numbers. So we'll write down that the Euler-Torsion function of 6 is equal to 2. Right, so this is how we define the torsion function. Torsion function is just a counting mechanism of the positive integers less than that number. I mean, if it is equal to that number, it is not co-prime. So less than that number, which are co-prime to or co-prime with the given number. This is how we define the Euler torsion function. Well, we'll return to this Euler-Torsion function in a while when we, like talk about if when we shall require a particular formula for that. But right now, we are not going to define the formula here, right? Okay. All right. So let's move to the next concept, right? The next concept that we are going to learn. Okay, before going that, maybe I must tell you that if we have, suppose another example, maybe if we have a particular number over here, which is a prime number, so phi of, let's say, 101, right? If it is a prime number, it is easily verifiable that the torsion function value is going to be 100, right? So since this is a prime number, this is a prime. If it is a prime number, this number is going to be the prime number itself minus 1. Okay, so this is the formula, because if it's a prime number, then there is no common factor of a prime number with any number smaller than itself except 1. 101 with, let's say, let's choose a random number like 27, right? So 101, the factors of 101, the divisors of 101 are 1 and 101. For 27, it is 1, 3, 9, 27. So the common is 1 now, right? So all numbers less than 101 are, each number less than 101 is co-prime to the particular number 101, and there are 100, exactly 100 numbers less than 101. So just we have just made a formula. So if there is a prime number, the Euler-Torsion function of the prime number is that prime number minus 1, right? Let's try to write that down in a more in a better way. So phi of n is equal to n minus 1 when n is prime. So this is a very important thing, very important um, expression that I would want you to remember, right? This is important. Okay. Yes, someone has unmuted. Is there a doubt that you would want to ask?
Yes, yes. Sir, in the first example, why didn't you take the torsion function of 6 is equal to 1 and why only 2, sir?
Okay, fantastic question. So let's look at the top pink colored um, statement there, right? So this is a definition of the torsion function. The torsion function counts the number of positive integers less than n, in this case n is 6, that are co-prime to or co-prime with n, which is 6, right? So first we are listing down all the positive integers that are less than 6. Positive integer 1 is less than 6, 2 is less than 6, 3 is less than 6, 4 is less than 6, 5 is less than 6. Now we will check which of these numbers are co-prime to 6, right? So 1 comma GCD of 1 comma 6 is equal to 1 and GCD of 5 comma 6 is equal to 1, right? Whereas GCD of 2 comma 6 and GCD of 3 comma 6 and GCD of 4 comma 6 are not equal to 1. So we are interested in those numbers, those positive integers less than 6, which are co-prime to 6. So 1 comma 6, 1 is co-prime to 6 because GCD of 1 comma 6 is equal to 1. 5 comma 6, GCD of 5 comma 6 is equal to 1. So 5 and 6 are co-prime, right? That is the reason we find out that there are two numbers, right? We have found out there are two numbers that are two integers less than 6 which are co-prime with 6. Hence, phi of 6 is equal to 2. Okay, I hope you understood. Is there a follow-up doubt on this?
Sir, I still did not understand this part.
Okay, let's take another example, right? Let's take another example and try to find out. So co-prime, right? So we are talking about co-primality. Before we jump down, can you say if 1 and 4 are co-prime or not? Is this a true or false? Are you there? It is Saima, right?
Yes, sir.
Okay. Can you tell whether 2 and 4 are co-prime? What is it? True or false? First one is true or false? The first one, the first statement says that 1 and 4 are co-prime. Is it true or is it false?
Sir, yes, it is true.
It is true. Okay, very good. All right. What about the second statement? 2 and 4 are co-prime. Is it?
No, it is false.
It is false. Okay. 3 and 4 are co-prime. Is it true or is it false?
It is true.
It is true. Okay. Now we will find with this information we will find out what is phi of 4. Okay. Phi of 4. What is phi of 4? This is the number of, right? Number of positive integers. Oops. Positive integers. Positive integers less than 4 co-prime to 4. Okay, is this definition fine with you?
Yes, sir.
Okay, so how many numbers are there which are co-prime to 4?
Two numbers.
Two numbers, exactly. That's how we counted the previous one as well. Here as well we did that. Okay. And we found out that okay, 1 and 6 are co-prime, 5 and 6 are co-prime. That's why phi of 6 is equal to 2.
Okay, sir, understood.
Fantastic. Let's now try to identify uh, um, uh, the next concept that has been that is to be used, right? Okay. Now the next concepts are already been discussed in huge detail in this particular module, right? We say that if a and b are integers and n is another greater than 0 integer, it's a positive integer, right? And these numbers are related in such a way that a is congruent to b modulo n, right? Then, right, if this condition holds, then there exists then there exists another integer q, which is an integer, which is a quotient, right? Such that A, which is the dividend, is equal to B, which is a divisor. No, B is not the divisor, my bad. N, which is a divisor. Q is the quotient, plus B, which is a remainder, right? Just as a small recap, I would want to mention these words here, but in small font. So this is dividend, this is the N is the divisor, Q is the quotient, and B is the remainder. Okay. All right. So we have got this relation, and we have solved a lot of problems in this. Cool. Now, there is one more concept on this particular congruency that we have just scratched the surface in some occasions. It's as follows. Okay. Now, this concept comes from the inverse of a number, right? So usually, when we say that, okay, what is the inverse of 5? We say it is 1 divided by 5, right? That is a multiplicative inverse. Then there is an additive inverse as well, right? Multiplicative inverse means you multiply a particular number by its inverse, you will get 1. Additive inverse is you add a particular number by its inverse, you are bound to get 0, which is the additive identity. Then there is an inverse in matrix as well. You multiply one matrix by its inverse matrix, you'll get the identity matrix. Identity matrix is a square matrix, which is also a diagonal matrix, and the diagonal matrix, all the diagonal entries are 1. So we have seen, come across a um, lot of inverses like that. But in this case, in our case over here, we are going to look into a different kind of an inverse. So this is called the inverse modulo n. Inverse modulo n. Right? So the statement goes as follow, right? The inverse modulo n of an integer a, right? A is an integer, right? We are always dealing with integer, by the way. It's like it's I may not write it down exclusively, but okay, is my screen visible, by the way?
Yes, sir.
Okay, yeah, I think it went off for a while. Okay, so a is an integer. The inverse modulo n of an integer a is congruent to we do not say equality, right? We say congruent. Is congruent to b if b is also an integer, by the way, right? If a multiplied by b is congruent to 1 modulo n. All right, so this is how it is. We have an integer a and an integer n. So the inverse of a modulo n is equal to b if this condition is true, right? So we can write this in an equivalent form. Equivalently, what we can say is that a inverse modulo n is equal to b. And we can also write it at another alternate method. B inverse of modulo n is congruent to a, right? So this is another important concept that we are going to use today. Okay, now before we jump to the algorithm, um, let's make a small revision of this Euler-Toshan function, right? In this Euler-Toshan function, there's an important definition that I had mentioned. The important expression here is uh, as follows, right? So we said that if n is a prime number, then phi of n is going to be n minus 1, right? Now, what if Now you see the fundamental theorem of arithmetic says that all numbers can be represented as products of primes. Let's say there is a number 8. 8 is 2 multiplied by 2 multiplied by 2, 3 times, right? 2 cube. 3 times we are multiplying a prime number 2. So 8 is a product of prime numbers. Again, let's see 100. 100 is a product of prime numbers also, because you multiply 2 with 2, you'll get 4. And let's see, 4 multiplied by 5 will give us 20, and 20 multiplied by 5 will give us 100. Whoa, wow. So we have got 2 multiplied by 2, 2 times 2 by the way, multiplied by 5, multiplied by 5, two more fives have been given and have been multiplied together. So two twos and two fives is equal to 100, right? Okay, let's say we have got another number, yet another number. Let's say 110, right? So 110 is 11 multiplied by 5 multiplied by 2, because 11, 5 multiplied 2 is 10, multiplied by 11 is 110. Yeah, exactly. So 110 is equal to 2 multiplied by 5 multiplied by 11. So every number, every integer, every positive integer, we're dealing with positive integers only, right? Every positive integer can be represented as a product of primes. So what we'll do here is we are going to write down the formula for phi n when, in a special case, when n is a product of two primes only, right? Okay, so so what we'll do is that we will write that down. Huh? So this n is a product of two prime numbers only, p and q. Let's say we say that where n is equal to p multiplied by q, and p and q are primes, right? So when this is the case, phi n will be p minus 1 multiplied by q minus 1. So again, this is an extremely important formula, and you are going to use this multiple times across whenever you are trying to solve RSA problems, right? So this is an important formula. Okay, so again, if I walk you through this, we take n as a product of two primes. Let the primes be 2 and 3, just for simplicity, right? 2, p is equal to 2 and q is equal to 3, right? So maybe what I can do is that we can just work it out on the top right corner, right? So p is equal to 2, q is equal to 3, so n will be equal to 2 times 3, which is equal to 6, right? Okay, I don't have space. N equal to 6. So phi of n will be p minus 1, which is 2 minus 1, multiplied by q minus 1, which is equal to 3 minus 1. So 2 minus 1 is 1, 3 minus 1 is 2, so 1 multiplied by 2 will get 2. Right? So phi of this is the formula for whenever n is a product of, whenever the number in question is a product of two prime numbers. Okay, now I think the entire setup has been done. The mathematical setup is done. We will now dive into the algorithm and try to understand how the algorithm is working. Okay, now again, the algorithm as a little recap of the algorithm, right? What we'll do is that we'll just look at the overview of what is happening, right? Okay. Now, for that, what we'll do is that we'll try to recall what had happened. We had a message, right? A message was there. The message is converted into a cipher, and the cipher is converted back to the message, right? The first process is called the encryption, and the second is called the decryption. So of course, like we will consider. I think I should write down a statement, small statement here, right? Consider M and C as numbers, right? When I say numbers, I mean integers, right? So in the back of our mind, let's put this idea and let's move forward. So, um, so first of all, so there are three algorithms that we are going to learn over here, right? So these three algorithms, if you remember, we had written, we had shown what those algorithms are. One of the algorithms is the key generation algorithm. The next algorithm is the encryption algorithm. Then we have got the decryption algorithm. To be very honest, the encryption algorithm and the decryption algorithm are quite similar to each other, whereas the key generation algorithm is a little tricky, right? So there are quite a good number of steps involved in the key generation algorithm. Okay. Um, so what we'll do is that we will first do the key generation algorithm because it's a little tricky part, right? And then once we get little uh, once we are habituated by doing those calculations in modulus, we'll come back to encryption and decryption algorithms and we'll look into that. So this algorithm is the RSA algorithm, right? And we are starting with the key generation. Key generation. Okay, now for this key generation, we need a few utensils, right? We need a few items for this. So I'll just write down the steps of the algorithm, right? And as we go along, we'll maybe take an example on the right hand side, right? Let me make some space and yeah, step one. Actually, I think I should mention the word algorithm here so that we don't miss out on anything. Okay. The key generation algorithm. Key generation algorithm. Okay. Uh, okay. Just give me a second, maybe. I'm trying to make some changes. Uh, so till now, if there is any doubt, please let me know. Any doubts till now? Anyone? Rahil, is everything fine? Okay. Since I'm not getting any response from anyone, let's proceed, right? Okay. So the key generation algorithm, what happens here is that uh, initially what we'll do is that we will choose primes, two prime numbers, P and Q, right? P and Q. On the right hand side, let's take two prime numbers. So can someone suggest two prime numbers, please? P is equal to and Q is equal to. People are there in the class?
Sir, P is 5 and Q is 7.
P is 5 and Q is 7. Fantastic. Thank you. P is 5, Q is 7. Let's choose two prime numbers. So this is step one. Again, as I said, it's a little like difficult when it comes to the fourth and fifth steps, but before that, it's really very easy. Number two. Number two is that we will find n is equal to pq, right? Okay. What would be n? N will be 5 multiplied by 7, that is 35. Okay. Very easy till now. Step 3 is also extremely easy. This is also find the torsion function of n. Again, you see here, this n is in the form of pq, right? N is in the form of pq. So we have a formula for that. If n is in the form of pq, we'll have a formula. What is the formula? The formula is uh, p minus 1, q minus 1, right? So phi of 35, let's write phi of n is equal to, uh, in the bracket, 5 minus 1 multiplied by 7 minus 1, which is equal to 24. Okay, so phi n, we have found out what the value of phi n is, right? Okay, now once we find out phi n, now the actual step begins, right? What we were trying to do is that we were trying to identify uh, what is the so you remember, uh, you remember that when we were talking about the person A and person B talking to each other through emails, right? The email ID is known to everyone, whereas the password is known to only the account holder, correct? So we are right now going to generate these two keys. One key which will ultimately be known to everyone, and another key which will be known only to the specific person. Okay, so the first key is called the public key, right? Fourth step, public key generation, right? So public key generation is very easy. In this public key generation, you just have to find a particular number E. So find a particular number E, and this E has to be uh, find E such that two conditions are satisfied. Okay, let me scroll this a little bit up. Yeah. Okay, the public key generation has got two steps over here. The E has to satisfy two conditions, such that the first condition is that E should be strictly greater than 0. Okay, E should be strictly greater than, it cannot be equal to 0, it cannot be less than 0. E is going to be an integer, of course. Now, and looking at this till now, E is a positive integer, and this value of E should be less than the value of phi n that you have received, that you have found out in the previous step, right? So our our key E, right, our key E should be less than 24, where it can be greater than 0. Okay, so we are finding out E over here, right? We're finding out E. That's the first condition. Now, the second condition is as follows. The second condition is as follows. The second condition is that the GCD of E, which is a public key, and phi n, which you have found in the previous line, has to be equal to 1. In our example, the GCD of E, 24 has to be equal to 1. And there is no restriction whatsoever. You can use any public key over here. Okay. There is one very small mistake that I have made over here. This is not 0. This should be 1, because 1 cannot be a public key. If 1 is a public key, nothing is secure. Okay. So we will choose. Oops, I again wrote 0 over there. So yeah. So we will choose a particular value of E which is greater than 1, strictly greater than 1, and which is less than 24, right? Okay, so let's identify one of them. If you look carefully, E is equal to 5 satisfies both the condition, because GCD of 5 comma 24 is equal to 1. On the right side of the screen, I have written that the GCD of 5 and 24 is equal to 1, because the factors or the divisors of 5 are 1 and 5, whereas whereas 5 is not a divisor of 24 at all, right? So the GCD of 5 and 24 is 1. So we can very safely say that, okay, the key used for encryption, E, that is a public key, right? For encryption, we can use this public key, right? A is sending an email to B. The world knows that, but they do not know what that message is. Because for that message, they need to open the inbox of A or inbox of B. They need to open those inboxes. Unless and until I open the inbox, I won't be able to read those messages. Okay, so sometimes some spurious email, malicious emails come to your inbox. When you click on that email, what happens is that there is something which happens, right? But the consequence is that there is maybe your email box, your mailbox is visible to someone else whom you have not given your password, right? So we need to identify a method by which only and only the password can open the login. Only that key can open the lock, right? So what we are trying to do here is we are identifying the public key E, which is greater than 1, less than the torsion function we have seen in the previous step 3, right? And we are going to identify that particular number. Now, once this is done, once the public key generation is done, we will move to the private key generation. You must have seen that when you are creating a new account on Google or on any other website, right? This and you are doing it from a browser. So mostly Edge browsers do this. Right? Microsoft Edge browser usually it does that. That it will suggest you some password. Not only Edge browser, there are some websites as well which provide like temporary passwords or um, like little difficult passwords, right? So they will suggest the password, and that suggestion means that okay, you are extremely safe, right? Your inbox it cannot be opened by anyone else except the person who has the password. Okay, now having said all of this, let's move on to the private key generation, the mathematical part of private key generation, right? I'll tell you that this is a little tricky part, right? And this needs a little bit of thorough understanding of the concept of inverse modulo operation. Okay, so public key generation. After that, there is a private key generation. Now, the private key is called D, right? The private key is called D. So find D such that such that D is equal to or D is congruent to E inverse uh, modulo phi of n, right? So phi of n is being used for this reason. So basically, what we do is that we take two prime numbers, right? We'll come to this example. We'll solve this, but before that, let's go through the entire thing once more. So first, we're choosing two prime numbers. 5 and 7 are the prime numbers we chose. Step number 2, we multiplied them. N is equal to P multiplied by Q. That gave us 35. Then we found out what phi n is. Phi n is since n is in the form of PQ, where P is 5 and Q is 7. So phi n is equal to 5 P minus 1 multiplied Q minus 1. So it is 5 minus 1 multiplied 7 minus 1. So it is 24. Okay, now the public key generation has got a few niche areas to look at. So one of them is that one condition is says that phi So the if E is the uh, public key, again E is the public key. So this public key has to be greater than 1 strictly and less than the torsion function value. Correct. Okay. And also there is a second condition that the second condition is that the GCD of the number E that you have chosen has to be the one, right? So the given function, the given value E and the torsion function should be co-prime with each other. Okay, having said all of this, we will move to the private key generation, and we'll generate the private key from this value E, right? So E is equal to 5, so D will be congruent to 5 modulo 24. 24. We're interested in finding out what is 5, what is D, right? So we know that the dividend D is congruent to 24x 24 oops 24x plus 5, right? So this is how okay, so I think this has got an inverse over here, d5 inverse, right? Plus 5 inverse. Now, now you see, like solving this is a little tricky because there is an inverse on the right hand side, right? So what you do usually is that instead of going for this kind of approach, what you can do is that you multiply both sides by 5 and then you open this up, right? You get my point? Okay, so instead of going by this road, what we'll do is that we'll multiply both sides by 5. We'll get 5d is congruent to 1 modulo 24. Okay, okay, 1 modulo 24. Now we need to find out a particular value uh, of d such that this condition holds, right? You will notice that d is equal to 1 will satisfy this immediately. D is equal to 1 will satisfy this immediately. Uh, D is equal to 5, right? D is equal to 5. So substituting, there are different ways of doing this, but I'm doing the most shortcut method. Substituting D is equal to 5, we get 25 is congruent to 25 modulo, oops, space branch. We get 5 multiplied by 5 is congruent to 1 modulo 24, and which is true, right? So since it is true, what we'll do is that we will write that down on the left hand side. So E is congruent to 1 modulo 24. Okay, so what we got here is we have generated a public key. The value of the public key is oops, this is not E is equal to, okay, so my bad. Mm, okay, D is equal to the final key is D is equal to 5. I think, yeah, that's enough. So D is equal to 5 is what we get. E is equal to 5 is this is the private key, and the public key is E is equal to 5, right? So in our case, these are the keys that have been generated, right? We'll take this example and move forward and try to encrypt a message, and I think we will get done till then. Okay, before moving ahead, I would want you to express any doubts if you have, please. Hello, Nandini. Is everything fine? Hello, Rahil. Things are going on fine?
Yes, sir.
Okay. Piyush, is it all fine?
Yes, sir.
Okay. Okay, Manas, I have seen your message. Private key generation. In the private key generation, what we are doing is a very simple process. We are trying to utilize the definition of inverse modulo of n. See, this inverse modulo of n says that if the inverse modulo n of A is congruent to B, if AB is congruent to 1 modulo n, right? So, in our case, we have the D, we have the E. E is there, right? E is there. We have found out the E in the previous step in the public key generation. E is equal to 5. Now, we want to find out the value of D. Now, the definition goes as follows. D is congruent to E inverse modulo of phi n. That is the definition. So, DE will be congruent to 1 modulo phi n. Now, the value of D is unknown. The value of E is 5 and phi n is 24. So, I would want to highlight this particular area where this equation has been written, right? So, from here, we want to find out the value of D. There are a good number of procedures to do it, but this is the easiest method just by plug and play, right? So you substitute D is equal to 5 here. The moment you substitute D is equal to 5, you get 25 on the left hand side. And we know that when we divide 25 by 24, we get the remainder as 1. And hence, 25 is congruent to 1 modulo 24. This entire statement becomes true. So D has to be equal to 5. Did that make sense, Mr. Manas? Okay, fantastic. So we have got D and we have got E. Correct? These are the values of these are the values. Let me write this down in a enter, pressing enter now. Yeah, so we have got these particular keys right now in our example, the private key and the public key, right? Public key and the private key. I will write that down in our example. Yes, please.
So can we find the GCD for no the keys for 7 and 24?
7 and 24 in the sense I don't understand what you're saying.
The GCD of 7 comma 24.
Yes, 7 comma 24 GCD is also equal to 1, isn't it?
Yeah.
Yeah. You want us to find out now?
Yeah, sir. So what will be the key for these two, E and D?
Correct. We will have to go through a different kind of a calculation in that case, right? Because 7 multiplied by 3 is 21. 7 multiplied by 4 is 28. 28 when divided by 24 leaves the remainder 4, which is not equal to 1. 7 multiplied by 5 is 35, which divided by 24 will leave a remainder double 1, 11, which is much far away. 7 multiplied by 6 is 42. 7 multiplied by 7 is 48. Yes, so 7 multiplied by 7 is 48, right? And then when you divide 48 by 24, you'll get a remainder 1, isn't it?
Okay, sir.
So if your public key is 7 in this example, right, then your private key is also going to be equal to 7. But these are all by plug and play, right? But there are methods to solve these kind of equations which are there in a different topic in the module, right? So we can refer to that process, those procedures there. We can do that in the scope of this class today, right? Okay. Now let's take a message, right? And let's say that what we want to do now, we'll take the input, the message, right? Encryption. So the encryption algorithm. I don't write the word algorithm. Take care. Encryption. So here the input, like let's make a small cartoon, right? So encryption. Let's mention that. Let's say that E is the algorithm, right? A small cartoon. Let's make, and there is a message. There's a message. Let's represent message by M. This message goes into the encryption algorithm. Along with this message, the public key, our public key. What is our public key? Small e is the public key that goes inside the encryption algorithm. And the product of those numbers n is also another input to this to this encryption algorithm. What comes out from the encryption algorithm is C, which is a ciphertext. Cipher or ciphertext, whatever you want to mention. This is the encryption algorithm, right? And at the same time, uh, just to give you a perspective, right? The decryption algorithm is also similar. The decryption algorithm, for that we need to input the cipher C into the decryption algorithm. Let's call the decryption algorithm capital D, right? Along with that, uh, see, in order to read the email, you need to open the account, right? In order to see your, reply to your notifications, or maybe send someone message on WhatsApp, you need to open your phone lock or your app lock, correct? So that is the decryption. That is the process of decryption. There is a hidden information, you are unhiding it. So for that, you need a password for that. Your fingerprint to open your phone lock or app lock or your facial recognition won't work if I handle that appliance. Hence, the decryption is always done by the private key. So there are, students usually make a little mistake in identifying which one to use where, right? Okay. Decryption is, there is information out there in the internet which is meant for you. Out there in the world, information is there which is meant just for you. Only you can understand it. Others will see it. Maybe there will be some who will be trying to open it up, but this belongs to you. That information belongs to you. So you will be using your private key, which is your password, fingerprint, facial recognition, to identify the message. Now, in order to do that, the input to this algorithm is a cipher, the private key, the number n, and what we'll get is the message m. This is how encryption and decryption is occurring. Let's take examples and see what is happening. Okay, now in encryption, right? Uh, as I said, M is there. M is the message, right? So what we do is that we write down the following formula. So we take the message and we raise the message to the power of the public key. All right. So let's take a message, for example. Let's say that M is a message. M is equal to, let's say, 4, right? Let's say M is equal to 4. So we take the message and raise it to the power of E. E is the public key. Correct? Now, M to the power E will take the modulo of N, modulo N will take the modulo N of that particular number, M to the power E, right? Modulo N means, what are we doing? We're dividing M power E by this number N, right? So, when we do that, whatever is the remainder, right? That will be our ciphertext. Example, this is the message, right? We can change this message anytime we want, right? So maybe I'll put this in a sparkling box. World Years Day. Okay, this is our message. right? So so C will be congruent to M is 4 raised to the power E. E was 5 and modulo N was 24, correct? So this will give us 1024 modulo 24, right? And this will give you how much? 1024 divided by 24. Mm, I don't know. What is the remainder here? Can anyone calculate it? In Python, you just need to type this one. You open a cell and you just type 1024 percentage 24 in Python. Is anyone doing it? Okay. Seems like no one is doing it. I'll try to see if I can do it. 1024 divided by 24, right? So 24 times 4 is 96.
16 is the remainder.
16 is the remainder, right? So 42 will give us 48 and 16 is the remainder. So we get the value as 16. So the cipher text is 16, right? So the original message was 4 and the number 4 got transformed to 16, right? So the original message was 4 and we got 16 over here. Okay. Now let's use the method of decryption to verify whether we can get 4 back from 16, right? So we'll let's do that. So decryption, the method of decryption goes as follows. Decryption, the method of decryption goes as follows. We'll find out M, right? M is what we have to find out. So this is also similar. C to the power D modulo N, correct? C to the power D modulo N. Now, now let's see what happens when we try to retrieve the message from the cipher. So the cipher was 16, right? And that to the power of 5 modulo 24. Any idea what this should be? Any idea what this should be? Again, in Python, this number would be 16 to the power 16. So in Python, the code is as follows. The code is as follows. Oops. The Python code would be as follows. 16 star star 5% 24 in Python. Yes, anyone? So I have got a Python. I have opened a Python and I'm going to solve it in Python, right? 16 star star 5 percentage 24 is giving me 16. Looks like there is a little error. Maybe we might have made somewhere. Anyone getting some other answer? 1048 576 percentage 24. Getting 16. We must have made some mistake on the way somewhere. Okay, I know where we have made the mistake. Guys, you see that we have to take n, modulo n, but we have taken modulo 24. 24 is not n, our n is 35, right? So all our calculations here are wrong. All our calculations are wrong. So instead of 24, let's write 35 here. 1024 modulo 35. So 1024 modulo 35 will be 9. So the message cipher here is 9. Correct? Okay. And of course, here as well, we'll take it as 9 to the power of 5. 9 is a cipher, modulo 35, and that will give us 9 to the power 5 modulo 35. So 9 star star 5 percentage 35. That gives us 4 again. Right? That gives us 4 again. Okay. So 9 is not 24. So 35. Let me make those changes here. Okay. So I think we are done with this particular exercise here, right? We have identified how to generate a key, right? Generate a key. How did we generate a key? Once we identified two prime numbers, these two prime numbers then helped us in getting the product of the prime numbers as n is equal to pq. Then we found out the Euler-Torsion function for that number n, which gave us 24. Once we got the number 24, we identified the public key and the private key. Right, so the public key is any number which is less, which is a co-prime to the Euler-Torsion number and less than the Euler-Torsion number, of course. So that is the public key, which should be known to everyone, which is the email address. We randomly choose that. But once we have chosen that, we will find out the inverse of the public key modulo the torsion function of the product of the prime numbers we had started with. So that will give us the private key. Once we get the public key and the private key, we are ready for encryption and decryption. Right? So the encryption process is basically in the algorithm we give input the message, the public key, the number PQ, and the cipher comes out as an output. When we are decrypting the message, we give the encrypted message as an input. We give this, which is a cipher. We give the private key as an input, and we give this small number n as an input, and the message comes out as an output. So the encryption and the decryption are similar methods. In this, what happens is that we take the message, raise it to the power of our public key, and we divide that big number by uh, the product of the prime numbers we had begun with, look at the remainder, and say that okay, that is the cipher message. And the cipher message is raised to the power of the private key d, right? So it becomes c to the power d, and divide that number by the product of the prime numbers n, and the remainder is the message m. Okay, so that concludes the RSA algorithm. We have understood what is the RSA algorithm. We demonstrated at least one example in this case. And before that, of course, before going to the algorithm, we revised through some of the important concepts that we have used in this RSA algorithm. And yeah, that's it. I have got some printed notes which I'm going to send over to you along with the script of this particular message. Uh, yeah.